So back to this. So we were talking about a linked stack implementation. It's another stack. I know this is going back to like Tuesday, right? A linked stack implementation. We're using a linked structure as our container, analogous to like the array, but because the array works differently than a linked structure, we're going to have a whole different setup. And instead here, size really is the number of things in the stack. I realize it kind of like top was the same thing in the array stack. But top, did double duty of the index of the next available spot. Well, here, that's not a thing. That doesn't make any sense. Here, what we're going to do is we're going to have a reference variable to a node of type t, where t in this case is little squares, is going to be a reference to the thing on top of the stack. If I want to push something onto the stack, I insert into the front. If I want to pop something, I remove from the front. That's the operations that we're going to do. That's the idea. So how do we start implementing? Well, public class link stack t implements stack. A link stack is going to be a stack. The array stack was a stack. The link stack is also going to be a stack. And anywhere you need a stack, you can use an array stack or a link stack. It won't matter. Because as far as I'm concerned, like on assignment 2, did you use an array stack, right? You used an array stack? I should be able to go to your code for assignment 2 and change half of one line of code. And I'll be able to use a link stack, and I won't need to change anything else. Half of one line of code. The half I mean is where you say stack, my maze solver stack, equals new array stack. I would change it to say link stack. But everything else would remain exactly the same, assuming the link stack exists. So public class link stack, it's generic. We have two reference variables, top and size. We don't need a default capacity because there's no array to have a default capacity of. And I guess we're not going to make use of a not found thing because we'll just have this flag of like, well, null or something. We'll see what happens. Then again, did we even have that in the links in the array stack? Because we didn't need to search the array stack, so I guess there was no not found. Yeah. Well, anyways. And then the constructor. We're only going to have one constructor. Whenever we make a link stack, it's going to start empty. So what should an empty stack look like? Well, its size should be 0 and the top should be nothing. There's nothing on the stack. We're not going to do any constructor chaining or anything because the only reason we had that for the array stack was, did we want the default capacity array or did we want some specified capacity? That's not a thing here. There's no array. So like the array stack, the link stack will implement the stack interface. The constructor creates an empty stack. So what would push look like? Okay, well, notice there's no like expand capacity. That's not a thing. What are we doing? Create a node called toPush containing the element I want to add. Because you could think like, well, the stack is all the elements. Well, the stack is going to be a link structure of nodes that contain the elements, right? So I'm going to return a Boolean, whether it was successful or not, push the element. Create a new node containing the element. toPush is next is top. Top equals toPush. Increase the size, return true. That's it. We can draw this. I've got top. It references something. I don't care what it is. It might be null. It might be another node. I don't care. I want to push. I make a new node to push. I put the element E in it. Just E, whatever. I know it's not really inside. It's a reference, but whatever. There we go. I say toPush, set your next to what top is. OK. Top, U equal toPush. Notice, I'm not saying top set next to toPush or anything. No. I'm saying top, the reference variable top, you're going to reference what toPush references, which is this. Insert to the front. There we go. This could be null. This could be another node. This could be a node followed by a billion other nodes. It doesn't matter. This is inserting into the front of a link structure. Increase size, return true. Again, this particular implementation, we're conforming to collections returning true when when they're successful. it'll only ever return true. It's not possible to return false, but just to conform with the standard stuff, we'll go with that. Any questions about this? Pushing is just inserting into the front of a link structure. How do we pop? Well, pop. Well, if it's empty, which we'll write in a moment, if it's empty, we'll do this like no such element. We'll raise an exception. You can't pop from an empty stack, just like with the array structure, the array stack. Otherwise, get the thing we want to return from top's data. Top, you are going to be top's next. So now, if I have right? All I'm saying is top, you're going to be equal to, okay, gets top's next. Well, this is top's next. So top, you reference top's next. There we go. That's it. Can you see that back there, or is this in the way? Can you see this? Yeah. Now, don't worry if this was, we'll use a dot to represent null. Top, which was a reference to this node, top equals top, get next. Well, top's next is null. Now it's empty. If there was one thing in the stack, this still works. If there's one thing in it, a million things in it, we're still good. Now, if it's already empty, well, we'll raise the exception. But if we make it empty, it still works just fine. Any questions about this? I'm getting a lot of blank faces. And again, I don't know if that's because you're happy, sad, this is way too easy, it's way too confusing. I gotta know. And now I'm just seeing nods, and I'm like, but that doesn't tell me. Thumbs up? All right, so you, and you speak for everybody. I asked, don't say I didn't ask. Right, so all it is, at the end of the day, this is just removing from the front. So what do we do? Let's make sure we're keeping track of everything. Get the thing from here we want to keep track of. Top, get your next. Decrease size, return the element. Pop returns the element if whatever we're doing, right? Cool. We are using this additional reference variable because otherwise if we lose track of top, we can't get its data. So we need to make sure we've got the data. If we did top equals tops get next, like if this was, and we said, okay, top, you were referencing this, and we say top equals tops next, and then I say, okay, go get the data from the old top, I can't. There's no way to get to it. I have no reference to it. I've lost it. So that's why it's important that we first get the data, then change it. Now I still have the data. That's why the order really matters here. Just being aware of like what our references are. And then peak. Peak's a much simpler version. Just if it's empty, raise the exception. Otherwise, return the data. We don't need an extra reference variable like we did up here because this ain't going anywhere. Questions or anything? Size and is empty. Well, size, just return the size. Is empty is, well, if size is 0. Can anyone think of another trivial way to check if it's empty? If top is null, it would be empty, right? If nothing's on the stack, top is null. So if top is null, it's empty. Also, if size is 0, it's empty. So both are entirely valid. What makes more sense? Well, this really is another case of, does it matter? No, but maybe spend some time thinking, if I have multiple ways to solve this problem, which strategy makes the most sense? I like this way because it's consistent with the array stack. If the size is 0, it's empty. If I see is top null, I have to know a little bit more about how the underlying thing works, where if the size is 0, it's empty. It's a little bit more obvious. It doesn't matter. Both would work, but I feel as if that's slightly nicer. Yeah?
I kind of forgot why. I feel like this was explained before. But why were you using like the size function instead of like the size
field, right? When in doubt, so at the end of the day, like I could have said size or the method or the field. Both would work just fine. So it was a little more obvious in the array stack. The motivation was clear in the array stack version. In the array stack version, it would have been top or size. And when you see size is 0, that's more obvious, but top, which did that double duty, the field top equals 0, you'd have to know a little bit more about the, oh, well, that's always the next available, so when top is 0. You'd have to know more. Now here, it's the same, so it doesn't really matter. But whenever given a decision, size is a private field. Obviously, it's accessible from within the class. But when given a choice, use the public-facing thing, even if it's internal, if given a choice. Does it really matter? No. The other benefit of using the public-facing thing is public-facing methods are tested in unit tests. Private ones aren't. In fact, if you go and you look at the array stack tests, there's no test for expand capacity. We only test the public-facing things. Now, if the private methods didn't work, the public-facing things probably wouldn't work either, right? But this would be tested. It's public-facing. There we go. Does it matter? No, but we had to make a decision. I didn't want to flip a coin. Does one make more sense? Yeah, I'll use the public-facing method, and here's my motivation. But if you did the field, no one's going to, like the Java police ain't coming for you. You'll be fine. But it's interesting to think about. These are like the questions that you often find yourself getting hung up on a lot. Like you will spend far too much time going like, well, you know, should I do that, this, naming your variables, is that a good name? That's not a good name. Like you end up spending a lot of time on this type of stuff when it really is design, not functional, but that's not a bad thing. It slows you down and it kind of like forces you to be very reflective of your code, which is very important because code is for humans, not computers. Machine language is for computers. Zeros and ones are for computers. Low voltage is high voltage. This is for a human. It's designed to be nice for humans. There's a whole program, a compiler in place to turn it into something for computers. So make your code as nice for humans as possible. Yeah? It was just a stretch or something. Yeah? Remember, stretched correctly. All right, toString. Well, remember, we're going to conform to how, like the order of the array stacks toString, where the top of the stack was the leftmost thing. Now, conveniently here, with the link stack, the top of the stack, the leftmost thing, is the thing at the beginning. So it's actually a little easier for me to go through and create the string version of this. So I'm going to use a string builder. Current node is top. While current node is not null, builder append the current node's data, the top at the beginning, a comma space, and then current node's its next node. And that's it. When we're done, give me the toString of the builder. Remember, this and this is the general strategy for looping over a link structure. While some current thing is not null, do something, current thing equals current thing's next. This is a simpler isn't the right word. Remember the array stack, how we had to do like the insert thing, where we were kind of like building from the front, but kind of like pushing, like adding to the front of the string? Now, by virtue of the fact that the top of the stack is the top of the stack is the thing at the front of the link structure, we can build it this way nicely. The array stack was different, right? But all of that is ultimately, as the user of the stack, all I care about is that when I print out a stack, the thing at the top is the leftmost thing. How it does that, I don't care. I saw people were doing, people were iterating over the array backwards. They were iterating over the array backwards, but were appending to the string builder. That works perfectly fine, right? With the array implementation for the toString. If you start at the end, but append on your string builder, that's the same as starting at the beginning, but prepending. What's happening under the hood doesn't really matter as long as we're conforming to what's expected, behavior and the interface and whatnot. Yeah?
That would be like E equals size and then E minus minus?
Exactly. For I starts at the length minus 1. Well, I is greater than or equal to 0. I minus minus. That's, yeah. Yeah. Is one better than the other? I kind of don't like for loops that count backwards, so I would probably prepend, but it doesn't really matter at the end, right? So there's the toString, and then the equal and the hash code. Well, the equals, we follow that same pattern. Is it literally the same thing? Is it null or not even the same class? Now, okay, convert it to a linked stack. If their sizes aren't the same, remember we used the arrays.equals for the array one? Well, we don't have a bunch of built-in static methods for the link structure, so we got to do that one like manually, so whatever. I know, right? But it shouldn't be too hard for us. First thing I say, well, are their sizes even different? This would have been implicitly checked by the arrays.equals static method that we used before. If their sizes are different, they're not equal. If one stack has 5 things in it, the other one has 55, they're not equal. But if they are equal, well, I've got this current, that current. Well, this current is not null and that current isn't null. Objects.equal. If they're not equal, return false. So start at the first two things. Are they not the same? If they're not the same, they're not equal. If they are the same, go to the next ones. Move down. So now we are iterating over 2 link structures at the same time, but like they're synchronized, right? You might look at this and be like, well, is it really necessary to check both? No. I know that they're the same size once I get to this line. If this current is not null and that current isn't null, it should never be possible that the number of nodes differ then, right? Meaning I really only need to check if one of them is not null. But for the sake of making your code a little bit more self-descriptive, I kind of like checking if both are not null. I'm guessing the compiler probably optimizes that away anyway, so it's not like we're wasting any like computation on checking both not being null. But yeah, it's just a linear search. And it's kind of funny, right? Because before, remember when we were doing a linear search, when you're going over one thing, it was as soon as you find the thing you're looking for, you can stop. Here, the thing I'm looking for is if they are not the same. So as soon as we find a pair that aren't equal, we stop. They're not equal. I can only conclude that the 2 link structures are equal if I go through and nothing wasn't equal. Pretty neat. And be mindful that this current is saying this current's next, and that current is that current's next. This and that, whatever. Any questions about this one? The hash code. What are we doing? Well, we hash the the size, and then we just iterate over the collection and get the hash code of each individual object. But again, we're doing the whole like iterate over the link structure. Same pattern, iterating over a link structure. That's how we iterate over a link structure. It is weird that like, okay, we're iterating over a collection, but depending on how the collection looks, we have to do it 2 different ways. It would kind of be nice if we had a common way to do it regardless, but it is what it is currently. We'll figure that out later. What I mean is when we wanted to iterate over an array, we liked the for loop. When we want to iterate over a link structure, we use this while, current's not null, and whatever. Any last questions before I carry on? Now, consider a doubly linked, okay. This necessarily requires a node class, right? Right? Now, what I'm about to describe to you is purely a design decision. It is not required, but I did it this way. I'm going to try to make clear really what I mean by that. But consider the problem of, look, we use singly linked nodes. We just call them nodes, all right? Where the node, each node had its data and its next. But we could make a doubly linked node where each node had its data and a next and a previous. We could do that. There's nothing wrong with that. In fact, maybe it'd be better if we did. A little later in the course, we're going to make binary tree nodes, which are often just called nodes. And this, again, it's just a node, right? Now, what type of node it is, you'd crack open the hood and you look. But at the end of the day, we like to just call these things nodes. They're just these like simple like units of structure that we use for something. Like when we built this node, we had it in mind for the link structure for a stack, right? It was built specifically in mind of being used for something else. So also consider that the node class would only be used for a linked implementation of something. Yeah, so this is what I mean, right? So like that node class that we made, the singly linked node, it can exist on its own. We used it on its own, like in the lab yesterday, where we just kind of built a link structure. But generally, if I'm making a node, it's to make a link structure for some like collection or something. So it's built really in mind of being used within another class, and only ever there. Because like this here, our stack, it's not returning nodes, it's only ever returning data, right? So as far as a user of a linked stack is concerned, they don't care about the existence of the node class. What do I care? The array stack, you didn't care about expand capacity. The link stack, I don't care about the nodes. I don't care if they're singly linked nodes or doubly linked nodes. I don't care. It doesn't matter to me. All I care about is if I can push, pop, peek as empty size and whatnot. So what we could do, we don't have to do this, but what we could do is we could say, look, this class only really matters, like this node class only really matters for the linked stack. So what we can do is we can actually define a whole class inside another class. In the same way that, look, we can define a function inside a class, a method, because it matters for that class, but not elsewhere, right? Well, the same idea for a whole class can exist. We're going to make nested classes. We already saw this in the JUnit stuff, where we had classes inside of classes inside of classes. But that was used in a very peculiar way. Here, we're going to use it in a more normal way, is we can actually define a node class inside the linked stack class, such that the linked stack can use the nodes, but outside of the linked stack, I don't care about the nodes. It's like making a whole, instead of a private method, it's like a whole internal private class. Again, this is not necessary, but it's a nice design thing that Java enables us to do. So yeah, we can put it inside the linked stack. If this is done, the node class can still be accessed from within the linked stack, but only accessible from within the class. So it keeps the node class out of the way of all the other classes. Yeah?
So does that mean that you just don't test the node class at all because it's private?
Yeah, that's right.
I like this.
Yeah. Going back to the doubly linked structure, a node class can exist within a class within a doubly linked structure. It will not introduce any ambiguity of one being called node, the other one being called node, but is it a single link, double linked, whatever. It's just, it's the node. It's this like little like unit of something important for the internal workings of this class. But instead of a single method, it's actually a whole class. So nesting in linked stacks. So what we can do is, below is an example of the nested node class at the end of the linked stack class. Notice both private and static. So we are making it a private static class. A private class, yes, but it's within another class. Node, private T data, private node T. But other than that, it's the same. This is just the node class, except we just copied it and pasted it inside the linked stack and turned it to private static. And if I go here, I think it'll be better if I just actually like open, yeah, here we go. Linked stack. And here's our node class, right? Private static. It's just in there at the same level as every method, but we just kind of tack it on inside of the linked stack. So we can use the nodes. This class is happy. It's entirely fine. Yeah. There is some nuance on whether you make it static or not and what it means, but in our case, this is what we want, and we're not going to get into all the nitty-gritty details because that tends to be a little bit more Java-y. But this is the general idea, is we can actually put a whole class inside of another class if it's important for the internal workings of this class, but not really anybody else. Pretty cool. And it also helps keep like our namespace clear, but let's not worry too much about that. All right. Now, what's cool here is if you look at this code, here's me just playing with a linked stack, right? What are we doing? We're creating a stack of integers called myStack, new linked stack, size, empty, whatever, just calling a bunch of these operations, just like this, okay? I'm just playing around with it, seeing if it interacts and it works the way we expect. What's neat is if we were to go back to the ArrayStack class, or the ArrayStack topic, scroll down to the bottom, you would see this exact same code with, again, half of one line of code being different. This would say ArrayStack. But everything else down here works perfectly fine because myStack, it's a stack. And Java's happy saying that this is a stack because it implements stack. Similarly with ArrayStack, this implements stack, so it's a stack. Because if you had like if I showed you this, right? Imagine I showed you this code, but I didn't, like I blanked this out so you can't see it. And you were to look at all of this, so my stack is a stack. Could you tell me, is this an array stack or a linked stack? You would have no way to know. All you know is that it's a stack. And that's exactly how we want it to be. Because the person using the stack shouldn't care about how it actually works under the hood. Again, we're learning this. We want to know how it works under the hood. Fine. But the spirit of what we're doing here, yeah. Neat, right? I guess I lied. There was one thing I didn't do here, was the whole, with the array stack, we like implicitly checked that expand capacity worked by making it a default size, and then tried pushing beyond that to make sure it actually worked, but whatever. It doesn't matter too much. Yeah.
Isn't expand capacity private?
It was. But we were like indirectly testing it, because if I made a stack where the capacity was 5, and then I pushed 6 things onto it, it better work. Right? If expand capacity worked properly, it would work. If it didn't, ugh. Yeah. Yeah.
What would be like the application differences for an array stack?
Like, why would I want one versus the other? Thank you for asking that. Let's talk about it. What a great question. So the question was, okay, we have a choice to make. Do we want an array stack or a linked stack? So what do? Well, first, let's take a step back and ask, what does it mean for an algorithm to be good? We kind of talked about this in 161 a little bit, right? Very high level, though. What does it mean for an algorithm to be good? Lines of code, how much space it takes up, how much time it takes. There's a lot of questions and things we could ask. But what does it mean for it to be good? What makes one algorithm for solving a problem better than another? Is it actually better, or is it basically the same? Is it actually the same algorithm, but it looks different, but it's not? All of these questions matter. Does the algorithm like have a practical runtime? I mean, like running for less time than the universe has existed? Or is it computationally intractable? Meaning like, well, in order to actually run this algorithm, it would take longer than the universe has existed, which we kind of talked about last semester, right? Which sounds like a silly thing to say, but I'm not being silly. That's literally something we can measure. And this happens with certain types of problems, especially when we get into the world of combinatorial explosion, where as soon as you add more things, it gets more and more and more complex. All right, so the questions can be answered. This question can be asked and answered in many ways, but at the end of the day, the big things we really want to know is like, well, how much time does this take to compute? Like how much computation resources? How much memory resources are required, like space? How many processors does this algorithm actually take? And does the amount of resources required change relative to the input size? These are questions we've talked about before. A linear search, how much more work do we do as the size of the input grows? These are the questions we've been thinking about. So time complexity. The amount of time, this is the big one. that we're really going to care about is time complexity. The amount of time an algorithm needs, now I don't mean stopwatch, okay? That's not what we're worried about. We're worried about scaling. Everything's relative to this like scaling thing. How much time does it take to sort 10 items versus how much time does it take to sort 10,000 items, right? If I double the number of input, do I double the amount of time it takes to sort? Turns out the answer to that is no, it's worse. But how worse? How can we measure these things? Can we like prove these things? And the answer is yeah, pretty easily. So consider the number of operations needed for an algorithm and the time complexity of those operations, like addition and comparison. Okay? A lot of what we were doing for a linear search, we're doing comparisons and addition. That's basically it, right? So with an understanding of the algorithm's time complexity, one can make informed decisions about what the right tool is for the job. So what data structure to use in a certain situation. What's interesting about this particular question, though, is the way, if I want to solve a problem and I say, I'm going to use a stack to solve this problem. Now, there are some problems where a stack makes sense, and there are some problems where the stack doesn't make sense. And there's some problems where you could use a stack and you can use something else. Your choice of data structure will affect your algorithm. And your choice of algorithm will affect your data structure. If I use a stack, I need to solve it this way. If I use a queue, I need to solve it this way. If I use a tree, I need to solve it that way. These things are all so interconnected. All right, cool? Any questions about, I'm just prepping you. So a growth function. So I'm going to describe things a little bit more formally. It's still going to be at 1,000 feet high, a fairly abstract level. These are concepts that you're going to spend more time thinking about in 255 and discrete math, or whatever it's called, 27, whatever. But I'm going to keep it fairly high level. And then we're going to go from this like high level formal decision or formal conversation to a much more concrete, simpler way to think about things. But it's important that we have the context. So we need to know and consider the relationship of the input size, n, and the amount of time the algorithm takes to run, T of n. T of n is this magic function that if I know the input size, T of n will tell me how long will this take, okay? So for example, the size of input could be the length of a list to be sorted. How does the time to run the algorithm, T of n, change relative to n? Now, T of n won't change, but the answer to T of n will change, okay? Like if T of 10 equals 10, and T of 20 equals 10,000, like, whoa. Like, what's going on here? Like, these are the questions that we're like thinking about, okay? Right? There we go. So T of n is called the growth function. And notice how T of n is a function of n. Consider this arbitrary growth function. This has no meaning. This has nothing to do with the stack or anything. I just pulled this out of thin air. T of n equals 15n squared plus 45n. Now, how we can derive a growth function, if I look at code, I might be like, well, based on this code, this is my T of n, right? You're going to ask me like, well, how do I go from looking at code to getting that? We'll talk about that in a moment. But let's pretend we've just got this magic growth function. If we look at this code, or this growth function, we start to think like, okay, let's break this growth function down into the parts. We've got the 15n squared, 45n, the sum of those parts. And then we've got this ratio here of how much this is relative to the whole thing. What proportion does this column take up over all of it? This is what we're going to be considering. Now we're running out of time and we need to do an activity. So for the sake, does anyone have any recommendations on what we should do for the activity today? No? I've got a good one, I think. How about, tell me how to push onto a linked stack. Write me the push method for a linked stack. That's what I want. Yeah, give me a push for a linked stack. That'll be a good one, I think.